Alright, today we will delve into Markov chains and we will see how they are used, what we can do with them, and how to model them when given a problem. Now, a Markov chain is actually they are a set of events observed at discrete times, because we are talking about discrete Markov chains, not continuous ones. So we have two parts to those chains. One of them are the states, and the other one are the stages, which are the times actually. So the states and stages will form the chains. Now, as you can see here, we have x0, x1, going on to xn and x infinity. These are states, observed states, at times from 0 to n. So this xo is the state of the system at the zeroth, the beginning, at the zeroth time. And this x1 is the, state of the system at the first time. So when you write xn is equal to j, you're actually talking about the system x being in state j at time n. So we have a system which is the x, as you can see, this one denoted with x. We have the time, which is denoted by n here, and we have the state. Okay, the what the system is doing, what's the current status of the system, which is the state j. Now, this is read as that at time n the system is in jth state, is in the jth state. So all states, all future states at least, depend on the state that's coming before it. Okay, just the one predecessor. Nothing else is important. For example, our system can be the weather. Okay, and the stages, the time is days. Right. So, for example, today is Thursday, so tomorrow is Friday. Tomorrow's weather is dependent on this day, Thursday only. We don't need to know about Wednesday, Tuesday, or Monday, or anything else before them. For the Markov chain, the only important part, the only important state is this state that we are in today. Okay, and what we will, guess, or how to forecast tomorrow is going to be dependent on today only. So, as you can see, if you write it like this, the system is in the ith state, in the nth time, this probability, given that all the previous states is actually equal to the probability for the one state, the previous state, the latest state we know about. That's it. So, as you can see, we don't need all the other states before the last state. The last state itself is enough, because this one is the last truth, last actual we know. Okay, so from here we have this probability, as you can see, p, j, k, m, n. Now this one is talking about going from state j to k in time from m to n. So for example, if m and n are only one time piece apart, 1 unit apart, then this will be the transition probability for one step. If there are 2 steps apart, this is going to be the transition probability for 2 steps, etc. We usually do this, we usually form this for one step only, and then just derive the others from that one, as you will see soon enough. So for all states in the system can have many states, usually finitely many, but it can have many states. And in this system, the states will have transition probabilities in all 2 pairs. It might even be 0. 0 is a probability as well, or it might be 1. Doesn't really matter. But all states will have probabilities between each other, even if it's 0. Now, this is the transition matrix. You see this one here, and this is the transition diagram. These are actually the same things, just they are being shown differently. The transition matrix is more, let's say, practical to use, easier to use, because we have to make some calculations out of them, and making calculations out of the diagram is harder, because transition matrix can just be multiplied by itself and other stuff easily happens there, but you have to just turn these values into matrix anyways. Now, in here, on the left-hand side, we have the initial state, the state that we are leaving, and succeeding state, the state that we are going to. For example, in here, for S1, for the first row, which is S1, we can see that we have the probability 0, P1, 2, and 0. Now, this means that the probability of going from S1 to S1 is 0. The probability of going from S1 to S2 is P1, 2, and the probability of going from S1 to S3 is 0. Now these values, they're all, they can all be different, all can be same, etc. But there's only one thing that's binding for them. All the sums in the rows should be equal to 1. So the sum of all values, all probabilities in this row is equal to 1. The sum of all probabilities in this row is equal to 1. And the sum of all probabilities in this row is equal to 1. There is no such concern, there is no such constraint for the columns, but only the rows. Why? Because if you are leaving a state, you have to go to a state. Okay, that's for certain. You cannot just leave the state and the system breaks down. No, you have to go to a state. So when you're leaving S1, you will either go to S1 or S2 or S3. There are no other options. So the probability of picking one of those, the total probability of picking one of those should be 1. Okay, but you don't need to say the same thing for returning to a state. Maybe you will never return to that state, so the sum will probably be in that position 0. So if you are leaving a state, you are going to a state, and this makes the total of rows equal to 1. That's for certain. Now, we can, just give a simple example for the matrix like this one. 0, 4, 0, 6, 0, 2, 0, 8. As you can see, the rows are 1, the total of the rows are 1, but the columns are not. Columns can be less than 1, the total can be less than 1, or greater than 1. It doesn't really matter. But they are still probabilities, so they cannot be all the units themselves. They cannot be greater than 1 or less than 0, because they are still probability values. Now, from here, we're going to check the types of those states and the subsets. Now, the states can be, they can have some types. They're going to be one of these at least. They can be transient, for example. Transient states are, as the name suggests, they are not there to stay, okay? They can be, they're not persistent. If you are in a transient state, given enough time, you may not be able to return there, ever. So, the transient states, there's a possibility that you will never be able to return to those states, okay? They're just, they're not permanent, okay? Those states are just transitionary, hence the name, transient. The recurrent state, on the other hand, is just the opposite of this one. It says that all recurring states will occur at least once during your travels, okay? Just assume that you are traveling through states in that system, and during those travels, those recurrent states, they will be able to, occur at least once, sometime in, the, let's say, infinite time spectrum. So, recurrent states can be reached during your travels. Transient states will not be reached at some point. Okay, they can be reachable for some time, but at some point, after some time, they will not be reachable. We will see what we mean when we check those, matrices. The absorbing state, on the other hand, they are the great nullifiers. When you enter an absorbing state, you cannot leave it ever again. All other states automatically become transient when compared to this one. If there are more than one absorbing state, they are not transient. They are absorbing states anyway, because in transient states, you have to be able to start on the state and then leave it forever. Okay? If it's an absorbing state, if you start in it, then you cannot leave it, so they're not transient. Okay? If you have more than one absorbing states, you cannot say that, okay, I have entered this first absorbing state, so the others should be transient. No, they're absorbing states as well. In transient states, if you visit one and then leave and never come back, if there's a possibility for that one, then it's a transient state. So, 3 types of states: transient, recurrent, absorbing. And now we have reachable states. These are actually state pairs from one state to be able to reach the other. If you can reach state A from state B, then state A is reachable from state B. Simple. If other way is correct as well, if state B can be reached from state A and state A can be reached from state B at the same time, then they are communicating. Now, this reaching doesn't have to be in just one step. For example, let's go back. As you can see here, from S1, I cannot go to S3 at one step, but from S1 I can go to S2, and from S2 I can go to S3. So S3 is reachable from S1. This is for sure, because I can go from S1 to S2, and then S2 to S3. So S3 is reachable from S1, and S1 is reachable from S3 because I can just go to S1 from S3 at one step. So they're communicating. And then we have the subsets. Now, in the subsets, we actually are talking about multiple states, which become a set of the whole state space. Now, these multiple spaces are called subsets. And if those subsets, if one of those subsets, at least one of them, cannot leave, let's say the system cannot leave any of those states and go outside of the system, then they are a closed system. This is just like the absorbing state, but now we have been absorbed by two or more states, maybe 3, maybe 4 states, okay? They form a boundary. They are like an absorbing state. When you enter them, you cannot go out, but this is made of 2 or 3 states. They are just, communicating with each other, and you cannot leave those states and go to another state ever again. So they are a closed state. If you enter that state, any one of those states in that closed subset, then you will be stuck there. You cannot go out ever again. And then we have the irreducible subsets. Now, irreducible means that you cannot, reduce those states. It means that there are no transient states in there. They are all communicating with each other. So if you start at one of those states, you can go to any one of them, and from any one of them, you can return to that state as well. So they're not transient. Okay, none of them are transient. They're all recurrent, and they're holding together. They're a closed set as well. You cannot go out from them. So they're an irreducible set. If the state space is irreducible, so all the states are irreducible together, then the Markov chain itself is irreducible. So we just call them irreducible Markov chain. Now, we also have a few examples of those. For example, absorbing and transient states. Now, there is a man walking along the road with 5 different corners, 4 blocks, so 5 corners. So we have corners 1, 2, 3, which are just on the road. We have corner 0, which is his home, and we have corner 4, which is a bar. If he is at any one of those corners from 1 to 3, 1, 2, 3, he will just pick a side with the same probability, with 1 over 2 probability, and go there. So from 1, he can go to 0 or 2. From 2, he can go to 1 or 3. From 3, he can go to 2 or 4. If he is at 4, which is the bar, he will stay there. And if he's at 0, which is his home, he will stay there as well. Now, this makes something like this. Let's just draw this one. Nope. Yeah, let's just draw it like this. So we have 0, 1. Let's start with a simple diagram, then we will see how matrix is formed. Now, these are 0, 1, 2, 3, and 4. Now, I can go from one of them to the other one. For example, I can go from 1 to 0, like this, or 1 to 2, like this. I can also go from 0 to itself. I cannot go anywhere else, because it says that if I reach 0 or 4, I stay there. So from 2, I can go to 1, or I can go to 3. From 3, I can go to 2, or I can go to 4. From 4, I can only go to myself. I cannot go anywhere. Now, as you can see, these are representations for the transitions in the states from one state to another. But this diagram isn't enough for me. I need to see the details. So I need the matrix. Okay, how am I gonna fill the matrix? I need to find the probabilities for all those arrows. For example, going from 0 to 0, this is probability 1, because there are no other ways I can go from 0. Same for here. Going from 4 to 4, again a probability of 1. Everything else is 0. Going from 1 to 0 or 1 to 2. Okay, these are equal, with equal probability. So these are 1 over 2, 1 over 2. Going from 2 to 1 or 2 to 3. Again, 1 over 2, 1 over 2. and going from 3 to 2 and 3 to 4, again 1 over 2, 1 over 2. So if I can just write them in the matrix form, I'm gonna get this one. Now as you can see, from 0 to 0 it's 1 probability. From 0 to 1, 2, 3 or 4 it's 0 probability. Because if I reach home, I will stay at home. I will stay at home. And if I reach the bar, I will stay at the bar. This is what it says. So these lines, these rows are pretty clear. Apart from that, we have to check the other ones. So if I'm at corner 1, I will either go to corner 0 or corner 2. So from 1, let me just clear this one. From 1, I can go to 0 or I can go to 2. Anywhere else is off limits. From number 2, I can go to 1 or I can go to 3. Anywhere else is off limits. And from number 3, I can go to 2 or number 4. And anywhere else is off limits, which is 0 probability. Now, which of these states, these 5 states, are absorbing and which of them are transient? Remember what an absorbing state is. If you go there, you cannot leave that one. So which of these are absorbing? Yes, 0 and 4. Thank you. So 0 and 4 are absorbing states because if you enter 0, you cannot leave 0 ever again. And if you enter 4, you cannot leave 4 ever again. What about 1, 2, 3? What are they? As the name suggests, they are transient states. From 1, I can go to 0 and never come back to 1. From 2, I can go to 1 and go to 0 and never come back to 2 ever again. From 3, I can go to 4 and never come back to 3 again. So they are transient. They cannot be, they cannot stay there. If you leave them, there's a possibility that you will not be able to return to them. For example, when you leave 1, you can go to 2. Okay, from 2 you can go back to 1, again to 2, to 1, 2, 3, and 4. Okay, now you cannot return back anymore. So there's a real possibility of not being able to return to 1 or 2 or 3. So they're all transient states. What about irreducibles? Ergodic Markov chains. Now, irreducible with an I, not an A, but okay. Now, in here, we cannot see any transient state, okay? These states cannot be reduced down, okay? For example, in here, these 3 states, 1, 2, 3, can be reduced and we can only have 0 and 4 because this chain is going to end at either 4 or 0. There are no other options, at least after some time. Again, same thing here. In here, we don't have any reduction possible because all of these states are recurrent. For example, if I start at 0, I can only go to 1. From 1, I can go back to 0 or go to 2. From 2, I can go back to 1 or go to 3. From 3, I can go back to 2 or go to 4. From 4, I go back to 3 immediately. So if I start at 0 or 4, I will just go back to the center mass, 1, 2, 3. And from there, I can go back to 0 or 4 once again. So this is an irreducible, which is all at the same time ergodic Markov chain. So we have talked about all these values are just one-step probabilities, okay? From going 0 to 0 in one step. But there are also 2-step, 3-step, or n-step probabilities as well. We're going to talk about them as well. So we need to find a way to, procure them, to find them. In here, for n-step transition probability, you can just take the nth order of the first step, one-step probability matrix, which is this one. For example, let's check to see this 2-step, probability matrix, how we are going to form this one. In here, we are starting from, let's just draw them so it's easier to understand. We have 2 states like this one, for example. Drawing is easier to understand and matrices are easier to calculate. So you can need both of them at the same time. From here to here, from here to here, and I also have 2 of those as well. Now let's assume that this is state 0 and this is state 1. Now I know that this probability from 0 to 1 is 1. Yeah. From 0 to 0 is 0. This is 0 probability. From 0 to 1 is 1. From 1 to 0 is 1 over 2. From 1 to 1 is 1 over 2 as well. Now, when you have this one, you can understand all the probabilities over here. When you have this one, you just have to take a look at how you can go from 0 to 0 in 2 steps. Okay. So from 0 to 0 in 2 steps. This one isn't here, so I cannot use this one because it has 0 probability. So from 0 to 1, I will go with 1 probability. And I have to go back to 0 again to be able to complete the 2-step process. So from 1, I will go back to 0 with 1 over 2 probability. If I multiply these two probabilities, I will get 1 over 2. So going from 0 to 0 in 2 steps has a probability of 1 over 2, which is 1 over 2. Let's find the probability of going from 0 to 1 in 2 steps. So I start at 0, I have to go to 1. To be able to stay at 1 for the second step, I have to, just do the loop and stay at 1 once again. So it's 1 times 1 over 2, which is 1 over 2 again. Okay. What about going from 1 to 0 in 2 steps? Okay, let's go from 1 to 0 in 2 steps. I have 2 rows. Going from 1 to 0 in 2 steps is either this one or this one. Now, I know that the one above 1, 0, 0 is a non-starter because going from 0 to 0 is 0. You don't have a probability of that. So this one is going to be 0. But this one, 1 to 1 to 0. From 1 to 1 is 1 over 2 probability. From 1 to 0, this part is 1 over 2 probability as well. So the multiplication is 1 over 4. So 1 to 0 in 2 steps is 1 over 4. Okay. What about 1 to 1 in 2 steps? Again, I have this one or this one. 1, 0, 1. So from 1 to 0, 1 over 2 probability. Back to 1, 1 probability. This one gives me a probability of 1 over 4. 1, 1, 1. Okay, 1 over 2, 1 over 2, 1 over 4. So 1 over 2 plus 1 over 4 is 3 over 4. It's over here. Now we can do this for large matrices as well, like 5 times 5 or, I don't know, rank n. N can be any number, 10, 12, 20, 100, a million. But still, if you are doing anything with more than 2, then you're going to have to waste a lot of time to get all the combinations, which is not logical, which is not possible, at least, given the time frame you're going to have. So the best way is not using this one, but using this one to understand what's happening, but just taking the power of the matrix. So if I take the second power of this matrix, I'm going to get this matrix anyway. So just multiply this matrix with itself, and you're going to get p squared, which is going to give you this one, which we have already found over here, with the diagram. But still, you need this one, to take the square of this one to find the 2-step probabilities. If you need 3-step probabilities, take the 3rd power. If you need 20-step probabilities, take the 20th power, which can be done with calculators and stuff, but still easier than just enumerating all of them. So taking the nth power is going to give you the nth order, PMF, nth order PMF. What else? Now, the nth order PMF, as I said, can be, let's just clear this one, can be calculated using the nth power, let's say, matrix multiplication. So take a look at this one. This is the starting matrix. It's just a given matrix, any random matrix. And we are calculating this, for the nth power and just squaring it, doubling it. We get p squared, which is this one. Now, we again take the square of this one, so I get p to the power of 4, and then take the square of this one, p to the power of 8. So from here to p to the power of 8, we got in 3 steps only. As you can see, if you take these, squares by itself, so just multiply this one with this one once again, so you got the 16th power of p, and you're gonna find you can do this for much larger numbers as well easily. Now, from here, we have to check a few things. The first one to check is there's something very obvious happening with the numbers over here, which is going to be explained later on, but still you have to see it. You can see that for the rows, check the rows, okay? 0, 32, 0, 33, 0, 50. 027, 029, 019, 021, 013, 015. All the numbers are dropping. Okay, same for here, for x1. 033, 025, dropping, dropping, dropping. And the inverse for here, 033, 025, 52, 48, 66, 63, 76, 74, growing. As these values drop, this one grows. Okay, we already know this should happen because their raw total should be 1 anyways. But how long will this keep going? How long will these numbers keep, shifting like this? They're going to keep shifting until they become 0, 0, 1, all of them. Okay, why? There's a simple explanation for that one. We are talking about long-run probabilities, okay? For long-run probabilities, you're talking about the state of your system at any given time, okay? You cannot really know this one, but you can have an inkling. You can speak with probabilities. There's a high chance, whatever that high chance is, that the state is going to be this one. You can just proclaim it if you know what you're doing. So what we are doing here is, if you take a look at the original matrix, you can be, obvious, it's pretty obvious, but you can be just sure that x2 is an absorbing state. And so x0 and x1, which can go to x2 immediately, so they are reachable, x2 is reachable from these two, so they become transient states. So x2 is absorbing, and these two are transient. So in the long run, you expect that state, the system, to be in the x2 state because it's the absorbing state. So it's going to come down to x2 at least once in any given time, and it will stay there forever. So this is actually going to 0, 0, 1. And this one is actually going to 0, 0, 1. So this is 0, 0, 1 already. So in the long term, you expect the x2 state be true forever. Okay, there can be no more any other states in there. Once we get to x2, we cannot get to any other states anyway. So what would happen if we try to find the unconditional probability, which means this one? Now, the diagrams here and the matrix here is all the same thing. It's talking about the same thing. We have two states, 0 and 1. And we are talking about the probability of A from going from 0 to 1 and probability of B of going from 1 to 0. Of course, we have 1 minus A of going 0 to 0 and 1 minus B of going 1 to 1, as you can see here. Now, from the third chapter, you probably remember this formula. We could talk about it, just a small reminder. We could say that we can write PA is equal to PAB plus PA B complement. Let's write complement like this one. I'm sure you remember this one. You could write this also like that as well. PA is equal to PA given P times PB plus PA. Let me just drag this out and yeah. That's not really, seen, but you can remember this one as well. Now, we were using these two to calculate the probability of A. So, in here we are going to do the same thing. Instead of A, we have xn is equal to 1. So, we are talking about the state being in 1, the system being in the first state at the end time. So, this is actually dependent on the stage before it. Okay, remember that the end stage is dependent on the n minus 1 stage. So n minus first stage. So it's over here. We can either say that the stage was 1 or the stage was 0. Okay, the state of the stage was 1 or the state of the stage was 0. In the previous stage at least. So from here, we can have this intersection or this intersection. Any one of them will be true. Both of them, depending on the situation, but still, any one of them will be true. So we will calculate these two formulas, these two probabilities, but we can just turn them into condition probabilities as well, like this one and this one. Now, this condition probability is something we already know about. This is the transition probability. So we are just going to look that up from the transition matrix. It's the same thing over here. This is a transition probability as well, so we can look that up from the transition matrix as well. So this one says that going from 1 to 1, As you can see, the state is 1 and the state is 1 as well. So going from 1 to 1 is 1 minus b. This one says going from 0 to 1. Okay, going from 0 to 1 is over here, a. So we're just gonna, replace those in, and we're gonna see that this is our, new formula. And then we can just take these into, just get the parentheses rolling and get them together. Now you know that n minus 1 is equal to 1. Okay, the probability of x n minus 1 is equal to 1. Let's call this P1. Then the probability of x n minus 1 being equal to 0 will be 1 minus P. Because these two, they're the same on the same row, so their total should be 1. Think about it. Either one of them is true. There's no other options there, okay? Either the system is at 0 or the system is at 1. So they are the same thing, okay? We don't care where they came from. The ending place is either two of them, okay? They're on the same row, we can say that. For example, it might be this row or any other row. We don't care which row is it, but they are on the same side, okay? So one of them has a probability, if one of them has a probability of P, then the other one has a probability of 1 minus P. So we can just write this one as this one, okay? So we are getting rid of the conditional probability part. Now, we have the long run probabilities, probably the most important part of the, this course, let's say, this part of the course, let's say. Now here, in the long run probabilities, we already know that we can just, multiply the matrix, the transition matrix with itself many, many times, okay? We would just be able to get lots of powers and stuff. But here, we're going to do it more elegantly without using those multiplications and a bit more easier. We're just going to have to solve a problem with, n plus 1 linear equations for n, unknowns, n variables. So we're just going to have to, do it more elegantly here. Now, we already know that we have some probabilities for each state, okay? And these probabilities are constant at, after an nth run, for example. So we can just say that if we have 3 states, okay, and after some time, all the rows are converging into the same state, same value. Remember this one? Now, in here, they're all converging into 0, 0, 1, okay? Because we know that these values will get smaller and smaller until they get to 0, and this value will get, these two values will get bigger and bigger until they get to 1. So we are going to converge to 0, 0, 1. Now, this convergence might take some time, so we might have to, keep multiplying matrices together, but we don't have that kind of time, so we prefer doing it in a more mathematical way, which is this one. Now, I'm not going to explain the formula, but you're going to see it in action and understand it, hopefully. But the important part is using this formula in the example is quite easy, but it might be confusing at times, so you have to keep applying a few times to to be able to get it down. So try to solve as many examples as possible by yourself as well. Now, a certain town's weather is classified each day as being rainy, sunny, or overcast. So we have 3 states. We just started with the states: rainy, sunny, overcast. But dry, overcast but dry is a continuous version of it, but okay. If it is rainy one day, then it's equally likely to be either sunny or overcast the following day. If it is not rainy, then there is 1 chance in 3 that the weather will persist in whatever state it is in for another day. And if it does change, then it is equally likely to become either of the 2 states. So, if it is rainy, then it's going to be either sunny or overcast with the same probability. So, it cannot be rainy again. If it's rainy, it can't be rainy again. So, if it's rainy, there's 1/2 probability of being sunny or 1/2 probability of being overcast. All right. If it's not rainy, it's overcast or sunny, doesn't really matter. But if it's any one of them, then there's a 1 in 3 chance that it will keep being the same in the same state. So if it's sunny, there's a 1/3 chance of being sunny again. And if it's not going to be the same state, then they are equally likely to be any of the 2. So it can be 1/3 sunny or 1/3 overcast or 1/3 rainy if it's sunny. And it's the same for overcast. If it's overcast, it can be 1/3 with probability 1/3 overcast or probability 1/3 rainy or probability 1/3 sunny. So all we have to do is just write these values into a matrix. Now here we will assume that rainy is the first state, as state 0 we can call it, and sunny is the second state, state 1, and overcast is the third state, which is state 2. But we don't have to call them like this. We can just call them, SO, stuff like that, RSO, rainy, sunny, overcast. But still, the first one is rainy. We know that we cannot have 2 rainy days back to back. So if it's rainy, having another rainy day has a probability of 0. So we start with a 0. If it's rainy, we have the equal probabilities for both sunny and overcast. So they are 1 over 2 together. So the first row is 0, 1 over 2, 1 over 2, like this. Now, the other 2 rows are all 1 over 3s. Why? Because we have already gone over this, but if it's sunny or if it's overcast, it's all 1 over 3 for the next state. Okay, for the next stage, whichever state is coming in for the next stage. So they are all going to be 1 over 3. Now, this is our transition matrix. Now, let's go back to the formula. The formula says that Pi is equal to the sum of P probabilities of Ji times P of J. Now, this one is actually calculated like this one. Let's just write those pi values. Now, this is pi 0 over here. This is pi 1 over here. This is pi 2 over here. Now, we also have the pi 0 over here as well. And pi 1 and pi 2. Now, both the rows and the columns have pi values in themselves, okay? We're gonna check them together. Now, for pi 0, to be able to calculate the pi values, you start from the column. Okay, we start with the pi 0 column now. We're gonna just have to calculate the value of pi 0, which is equal to 0 times pi 0 plus 1 over 3 times pi 1 plus 1 over 3 times pi 2. Now, pi 0 will be equal to the sum of these values, these multiplications, which, as you can see here, pi 0 is equal to 0 times pi 0, which is gone, omitted, 1 over 3 times pi 1, and 1 over 3 times pi 2. Same thing for pi 1, 1 over 2 times pi 0, as you can see here, 1 over 3 times pi 1, and 1 over 3 times pi 2. And again, for pi 2, we have 1 over 2 times pi 0, 1 over 3 times pi 1, and 1 over 3 times pi 2, which can be seen here. Now, from here, we have 3 unknowns and 3 linear, equations. Can we solve this problem? Is this problem solvable right now? Can we find values for P0, P1, and P2 with 3 unknowns and 3 linear equations? Do you remember this? Okay, I guess no answer. Actually, in reality, yes, if the equations are linearly independent. But if they're not independent, then no, you cannot find an exact answer to that one. And these 3 are not linearly independent, like ever. Okay, so we already know that we cannot find a solution from these 3 equations. We need a 4th one. Do we have a 4th equation? We actually have a 4th equation. We know that the sum of these pi values should be equal to 1. So we have another equation. Pi 0 plus pi 1 plus pi 2 is equal to 1. Hence, we're going to use that one as well. So from here, from these equations, we will find that pi 1 is equal to pi 2. And from there, we're going to find, when we replace pi 1 over pi 2, we're going to find that pi 0 is equal to 2 over 3 pi 1, which you can see here. We also know that the sum is equal to 1. So I will just say, okay, pi 1 plus 2 over 3 pi 1 is equal to 1. So from there, we can find that pi 1 is 3 over 8, which means that pi 2 is 3 over 8, which also means that from here, pi 0 is 2 over 8. So we have found our probabilities, 2 over 8, 3 over 8, and 3 over 8. We can find it like this, okay? So this means that in the long run, any day we pick will have 2 over 8 probability of being rainy, okay? Which also means that if we pick 8 days in a row, we expect 2 of them to be rainy from expected value. So if we pick 8 days in a row, we expect 3 of them to be sunny and 3 of them to be overcast. This is what it means, okay? These long-run probabilities, how they are, let's say, explained. So what about the other way? Couldn't we have just, multiplied the matrix by itself till we get, equal rows on all around? Yeah, we could do that. For example, the first one multiplied by itself gives this one. If you multiply this one by itself, we will get this one. Another multiplication will get us this one. Another one will get us this one. And another one will get us this one. Now, we have done 5 multiplications, 5 matrix multiplications to get here. And here we are certain that it's going to be, 2 over 8, 3 over 8, 3 over 8. It's very close to that one, so we can be sure, 95% sure at least, and say that, okay, this is going to give us 2 over 8, 3 over 8, 3 over 8. But the time spent doing those multiplications is much, much, much greater than just doing these calculations, okay? Those matrix multiplications are going to take so much time that we don't need those, so this is easier. But you can use both of them, of course. It's all up to you. Another important part of those, matrices, those, Markov chains, is the expected time of passage. This is, the time we expect to pass when we are traveling from one state to another state. Now, this can be anything, between 1 and infinity, I guess, but still, or 0, if we are trying to travel to the same state from the state we are in, it's 0, we're not going anyway, we're in this true state anyway. But as you can see, as long as these values are, different, the same, they are just 0. But if they are different, we have to calculate using this formula. Now, this formula is actually the same formula we have used in the 7th chapter with the expected value, loops. Remember those, the recursions? It's the same formula actually, but it's a bit more, mathematically composed, let's say. The one here, remember the EX formulas? EX is equal to some probability times 3 plus EX plus some probability times 5 plus EX. We had those formulas. Remember the minor question? It's the same thing, but the way we travel is just 1 unit. The distance is always 1 here, because we get from one state to another in 1 unit time. So the distance is always 1 here. 1 plus, probability times the expected value, because these m's are expected values. They are the expected passage of time, as you can see here, expected time of passage. So what we are trying to calculate is an expected value, and we are going to try to calculate it using this formula, which you will understand perfectly when we get to the example. Now, we have 4 states. The first state is an absorbing state. As you can see, if we come to the first state, we are not going anywhere. We keep looping to ourselves. And the 4th state is absorbing state as well. If you come to 4, we're just looping on ourselves. Okay. Now, we're going to try to find the expected time to absorption if we start the process at state 2. So, starting from state 2, we're going to try to get to absorption. Now, the absorption happens only on 1 and 4. So, if you want to find the absorption, we have to get from 2 to 1 or from 2 to 4. So, we'll just try to calculate the absorption of 2 to A. So, it's M to A. We are trying to find M to A. Now, to find M to A, I have to start from 2 and check all of its neighbors. I'm just going to write this formula and check all the neighbors. Okay. It's 1 plus, let's forget about the 1 right now, from 2 to 1. The probability is 1 over 2. 1 over 2 times M1A. As you can see here, the probability of going from 2 to 1 or 1 to 2, it's the same thing here for J to I to J. But still, from 2 to 1, and then the minimum passage of time from 1 to A. So as you can see, this I is 2, this J is 1. So we are going from 2 to 1, and we are checking the absorption of 1, the first state, M1A. Now, M1A is 0, so it's going to drop anyways. So I have to check the other side as well, the other neighbor. So I have 1 over 2 once again, and M3A, which is an unknown. I'm going to have to calculate this one. Just leave it like that. Now, for M1A and M4A, we have 0, because they are the absorbing states anyway. For M3A, it's either 1 over 2 times M4A, which is 0, and it's going to drop, or plus, which means 1 over 2 times M2A, and plus 1, of course, the step size. Now, when we simplify these values, as you can see here, M1A is 0, M4A is 0, M2A is equal to 1 plus 1 over 2 M1A plus 1 over 2 M3A, and this is going to drop because it's 0, and we have this one. And for M3A, we have 1 plus 1 over 2 M2A plus 1 over 2 M4A, which is 0 once again, and it's going to drop. So we are left with this simplified version. So from these two, we know that we can just replace one of them with the other and find that M3A is 2. And from here, we can see that M2A is 2 as well. As you replace this one, as you can replace this one with 2, you'll get the 1 plus 1 is equal to 2. Now, this is the absorption state, going to the absorption. What if we didn't have any absorbing states? What if we just wanted to find the distance, the mean expected time between two states, any two states that are not absorbing? Then we can just check the same, we can use the same formula and check to find the, expected distance to the final state going through all other states. For example, if you are trying to go to from 1 to 2, okay, we're just gonna start with 1. We can say that it's M12. Okay, we are looking for M12. M12 is equal to 1 over 2 times M22 plus 1 over 2 times M32. So this is actually 0, so M22 is going to drop. So we have 1 over 2 times M32 plus 1, the step size, like this. Now, M22 is 0, we already know that. M12 is calculated using this formula once again, 1 plus 1 over 2 times M22 plus 1 over 2 times M32. This drops, so we have this one. And we have to calculate this one as well, M32 as well. So we write M32. So from M32, we have with 1 over 2 probability going back to 1, which is M12, which is going to be the time M12. Or with 1 over probability, we're going to go back to 2, which is going to be M22, which is 0. And of course, plus 1 as well, because we are taking that step anyways. Now, from these two formulas, we can just replace them with each other, and we see that the M32, which is also the M12, is equal to 2 steps. This is the expected value. Okay. How else could have we done this? There are other ways of doing this. For example, I'm trying to go from 1 to 2, right? Okay. I can go it in 1 step. Yes, it's a 1 over 2 chance of going in 1 step. All right. There's also a 2-step rule. 1, 3, 2. So there's a 1 over 4 chance of going in 2 steps. Okay, 2 times 1 over 4. Cool. There is also a 1 over 8 chance of going in 3 steps. Okay, how does that go? From 1 to 3, back to 1, and then 2. 3 steps, 1 over 8 chance. Okay, 1 over 2 times 1 over 2 times 1 over 2. There's a 4-step way for 1 over 16. From 1 to 3 to 1, back to 3, and then to 2. 1, 3, 1, 3, 1, 3, 2. 1, 3, 1, 3, 1, 3, 1, 2. There are lots of different ways. They all have different step sizes, and they all have different, probabilities. But all we have to do is just multiply those probabilities with those step sizes, and then just sum them. This is what the expected value is about. So we have a series summation there. If we can find the value for the series summation, we're gonna get the solution we're looking for, which is gonna be 2 steps once again. So this exercise was a bit confusing during the exam for the students, because the most important part is the modeling part here. So if you cannot model the question given to you into a transition matrix, if you cannot change it and write the transition matrix correctly, you're gonna solve the question wrong. There's no doubt about that. Now, this is actually very if you can understand the English part correctly, it's very easy to solve, but the understanding part is the easier part here. Let's take a look. Consider an inventory system in which the sequence of events during each period is as follows. First, we observe the inventory level, call it I, at the beginning of the period. Okay. If I is less than or equal to 2, 4 minus I units are ordered. Okay, let's take a look. Less than or equal to 2. If it's 2, I'm going to order 4 minus 2, 2 units, and I'm going to have a total of 4 units. If it's at 1, I'm going to order 3 units and get to 4. If it's at 0, I'm going to order 4 units and get to 4. So if I am below 2, equal to or less than 2, then my level of inventory will jump to 4 instantly. And then I will start getting orders from my customers. So let's take a look. 0 units are demanded during the period with probability 1 over 4. 1 unit is demanded with probability 1 over 4. and then with probability 1 over 4, 2 units are demanded, and with probability 1 over 4, 3 units are demanded. So all demands have the same probability 1 over 4, and there can be only at most 3 demands. Okay, 0, 1, 2, 3. And then we are asked to define a period state to be the period's beginning inventory level. Okay, now think about the periods. Let's call them January and February. Let's go with months. The end of time, the end period or ending inventory of January is the starting inventory of February anyway. So for any period, the ending inventory will be the same for the next period start. Okay, this is how it goes here, how it goes in most cases at least. So when we think about it, we're gonna have to find the amount of inventory we can have in our, let's say depot, storage, whatever. These amounts are going to be our states. So we always know that we can have 0 inventory, which will be upgraded to 4. Okay, 4 is the most inventory I can have then, because at 4, if I don't, give anything to customers, I will have 4 again, and I will not order anything new. At 3, I will not order anything new. At 0, 1, 2, I'm going to upgrade it to 4, but in the other ones, I'm not going to use anything. That's good. This is still start of the period though. We haven't gotten to the, end of the period yet. This is start of the period. So we are selling things now. All right. If I had 0 inventory, I would have 4 inventory right now. So from 4 inventory, I can get 0 or 1 or 2 or 3 pieces of demand. Now, if I get 3 demand, I will sell all those 3 from my 4, and I will have left with, I will just have 1 unit of inventory at the end of the period, which will mean 1 unit of inventory at the start of the next period. So from 4, I can go down to 1. Okay, from 4, I can go down to 0. No, I can't, because I don't have a demand of 4 ever. From 4, I can go to 2. Yes. From 4, I can go to 3. Yes. From any other side, it's all the same, except for 3 units. At 3 units, I can go down to 0. For all other starting inventory amount, I will have to upgrade it to 4. Anything less than 3, I will have to upgrade it to 4. If it's 4, it's already 4, so no problem there. And from 4, I can only go as low as 1, because my maximum demand is 3. So I'm just going to have to write the states in the matrix in 5, pieces. Let's see, 5 rows and columns. From 0 to 4, from 0 to 4. We already know that if we are starting with 0, with no inventory, we are upgraded to 4 instantly. So from 4 inventory, I can have 3, 2, 1, or 0 demand with all the same probabilities. So it's going to give me 0.25 probabilities for all these values, all these transitions, okay? It's the same for 1 and 2 as well, because they're all upgraded to 4 instantly as well. And it's the same for 4, because it's 4 already. So for 0, 1, 2, and 4, I cannot go back to 0 in this next stage, in next time period. I can only go to 1, 2, 3, or 4, and they with equal probabilities. But if I am at 3, pieces of inventory, then I don't upgrade to 4. I'm just selling them, and I'm saying that, okay, if I sell all of it, I can go to 0, which is a probability of 0.25. But I can never go up to, inventory of 4, because from 3, you can only go down, okay? You will not upgrade till the next term starts and goes underway, okay? So there's no upgrading it. If I sold 1, I will upgrade to 4. No, you won't. Not in this period. It's in the middle of the next period, so it's not going to work like that. We are talking about start of period inventories, okay? So at 3 points, at 3 units of inventory, we will have any value but 4 for the next start, next stage. So this is the transition matrix. Okay, find the steady state of the chain. The steady state is the long run probabilities. Okay, the pi values, pi 0, pi 1, pi 2. That's the steady state. That's what we call the steady state. So we're just gonna have 2 ways over here. Either multiply this matrix by itself, until you get a steady state of rows, or just use the pi values. Of course, we will use the pi values. And after using those pi values, we're gonna get these pi, we're gonna use those pi formulas and we're gonna get these pi values. So pi 3 is equal to 6.25%, pi 2 is equal to 25%, pi 3 and pi 4 are 25% as well, and pi 4, pi 1, pi 2, pi 3, 25%, and pi 4 is equal to 18.75%. Now, these values are our expected, probabilities. In the long run, this is what's gonna happen for us, we say. Okay, and then part C asks, if at the beginning of each period, we have to pay $1 for each unit in inventory. Okay, now we are talking about expected value. What's the expected inventory cost per period? So we have to find the expected value, which was X times PX. Okay, cool. My X is, for this one is 0, because I have 0 inventory. For here, my X is 1. For here, my X is 2. For here, my X is 3. And for here, my X is 4. If I multiply all these with their X values and sum them, I will find the average inventory, size for any period. Okay. Then all I have to do is just multiply that with 1, because it's $1 per inventory. So I'm gonna get 2.25. So once you understand the question, what the question is asked and how it's gonna be solved, it's not that hard. The hardest part is just writing these, matrices correctly, and it can be done if you, work on it, if you practice enough.